So the aurora borealis and the aurora australis are great visual opportunities to recognize the amount of energy that is actually reaching the surface of the earth through the penetration of the magnetosphere. And these are most apparent on nice dark clear days, and we don't get a lot of those in Ohio, so we don't get the opportunity to see them. And so I've introduced a couple of videos for you to take a look at how the aurora are produced, and how and what they look like and how extensive they are. But for the most part, what we see is the energizing of atoms in the atmosphere, primarily some oxygen atoms and nitrogen atoms. As the photons hit these atoms, they start to excite these atoms, and what we get is this display of light across the atmosphere. The color is indicative of which molecules are being excited. It's probably a good opportunity at this junction to say that the colors that we see in the visible light spectrum are a product of the wavelength that is being bounced back or refracted back from the object. When light hits an object, that object's going to absorb energy, some volume of energy, and it's going to refract energy back out. And it's refracting a great volume of energy out, but the only volume that we are privy to with our natural optic nerves is the visible light spectrum. So we see that as color. So if you are wearing a red shirt, energy is being absorbed in the visible light spectrum. The blues, the oranges, the yellows, the greens all get absorbed, and what is being sent back to your eye is only the red of your shirt. For instance, there are lots of other spectrums being sent back out, but they are on either side, either longer or shorter than that green spectrum that we're able to see. Or I said red, right? Red shirt. All right, so with the visible light spectrum, it sits right in the middle of the electromagnetic spectrum, as you can see in this chart here. The electromagnetic spectrum, cosmic and gamma rays are our fastest wavelengths, and then we move through to longer and longer or less and less dangerous waves as we move through to the longest waves, which are radio waves, which can be kilometers long in length. The length of a wavelength is measured between its troughs or its crests. So and you can measure either a trough or a crest. The length is going to be the same, but the crest is the arcs on the top of the wave, and the crests are the arcs on the bottom of the wave. The faster the wavelength, the shorter the distances between those troughs. And that's when things get dangerous, is when they're short, because the photon of light is going to hit more frequently a location, not allowing that location to recover, or permanently damaging that location genetically. So this is when we get skin cancers and things like that from UV light. So the frequency then is how many troughs or how many crests pass over a second. And we measure the wavelengths in that regard. So solar energy coming in, being absorbed and re-radiated by atoms and molecules in the atmosphere, are going to then generate weather and climate. And the difference between weather and climate is duration and an average set of characteristics. So weather is what's happening at a particular location at a particular moment, and that can change from moment to moment. We've all lived long enough to know that a morning can be gorgeous and an afternoon can change on a dime and have unexpected weather conditions. Weather, for the most part, is temperature, precipitation, humidity, and wind. Wind, precipitation, and humidity are all the byproduct of energy, and temperature is a proxy to how much energy is in the atmosphere. All right. Climate, on the other hand, is what are the general characteristics of weather that happen consistently over a period of time. So you would probably have certain expectations of what you would expect for the weather to be for the second, third, fourth week in January. If the temperature gets exceptionally warm, or we get large rain showers, you would probably think that that is unseasonal and that doesn't fit with the climate of the area. And you would probably be right. In order to recognize climate, we measure the averages of weather over statistically long periods of time. The longer the period of time, the more statistically stable that is, but it doesn't give us insight onto how climate may or may not be changing. Is it getting wetter or drier or warmer or cooler, or are all of those variables over different time periods? Are the springs getting warmer but the fall's getting cooler? Are the summers getting drier but the winter's getting wetter, right? So all of those things can be in play. Generally, an individual who's wanting to recognize if things are changing wants to take the shortest average period that they can model in order to see if change is occurring, because it's important for society to be prepared for change. Are we going to need to consider more hospitals if the change is going to mean we're going to have more hot days, which means maybe more respiratory distress? Are we going to need to augment or change our infrastructure to accommodate more rainy days so our roads do not get overwhelmed with precipitation? So it's important to stay on top of changes in climate and weather over time. So 30 years is what we use. And so we look at a 30-year running average, and the 30-year running average will tell us if there are anomalies occurring that we don't need to be concerned with, or if those anomalies are going to turn into trends that we're going to need to take note of and make changes for. So for this year, we're looking at the averages, measuring every weather variable every day from 2020 through to 1990. That's our 30-year average. Prior to that, last year, we went from 2019 to 1989. Next year, we're going to go from 1991 through to 2001. So we've got what we consider a running average, and therefore we can take these blocks of 30-year periods, and if there are anomalies like there was in 1990 with the eruption of Mount Pinatubo, which cooled the planet for 4 years, we can take those anomalies and they get absorbed into the average, and we recognize that those are not long-standing climate changes that are occurring. We're only concerned with the changes that are occurring and not the anomalies. Certainly a longer length of time would be better, 100 years, but we lose the nuances. We would like to go below 30 so we can react faster to change, but those 20-year or shorter periods of time don't give us statistical confidence, so we go with 30 years. All right, I'm going to start the next slide set with temperature controls.